Dear students, we have already discussed about an important concept called electric field. Around a charge, whether it's positive or negative, there exists an electric field. And this field is extended till infinity. And the existence of the field can be visualized easily using a concept which was introduced by Michael Faraday, and that concept is called electric field lines, introduced by Michael Faraday. So, Michael Faraday introduced this concept of electric field lines. So, what is the advantage of these electric field lines, or what are the uses of these electric field lines? With the help of electric field lines, we can understand the nature of the field. Now, what do you mean by nature of the field? Whether the electric field is a weaker field or a stronger field. We can even find the direction of the electric field. We can even find the location or the position where the net electric field is 0. So, these are the advantages of electric field lines. So, now let us learn what exactly an electric field lines and what are the properties of it. An important question, as you can see, it has appeared 6 times in the examination. So, first, what is an electric field lines and what are the properties? So, that is what we are going to discuss right now. So, one after the other. Now, to understand electric field lines, I am going to consider a positive charge plus Q, and you place a unit positive charge here plus 1 coulomb. In which direction this unit positive charge tends to move because of the interaction with the positive charge? Like charges, they repel. So, therefore, this positive charge tends to move in this particular direction. So, you draw a line with an arrow. Now, whatever that line which we have drawn with an arrow indicates electric field lines. Do they really exist? No, it's imaginary. So, what is an electric field lines? An electric field lines is an imaginary path along which a unit positive charge tends to move. So, that is the statement of electric field lines. An electric line of force or electric field lines, electric line of force is another term used for electric field lines. An electric line of force in an electric field is an imaginary path along which a unit positive charge tends to move. Suppose if I place a unit positive charge here, it tends to move in this direction. If I place it here, it tends to move in this direction. So, wherever you place it, it tends to move in that particular direction. So, this is how we can draw lines of force around a positive charge. What if the charge is a negative? Then place a unit positive charge and then see in which direction it tends to move. It tends to move in this direction. So, therefore, draw the line of force like this. Place plus 1 coulomb. In which direction it tends to move? It moves in this direction. So, draw the lines of force like this. So, this is the line of force around a negative charge. Now, what we can understand out of this? So, first we will come to know every line that is drawn indicates the direction of the electric field. See, all this represent the direction of the electric field. And then, if you see the space between them, it continuously increases. See, here it is least, here it is increases. That indicates that as we go away, the strength of the field decreases. The field is non-uniform, not uniform. Then, if it is uniform, then how to draw these lines of force? If it is uniform, then we draw parallel lines with equal spacing. So, this is the representation of uniform electric field. This is the representation of a non-uniform electric field. So, if the lines of force are not parallel, then the field is not uniform, non-uniform, and if the lines are parallel with equal spacing, then the field is uniform. So this is how we can visualize the existence of the field, and that concept was introduced by Michael Faraday. So what is an electric line of force, or what are electric field lines? An electric line of force in an electric field is an imaginary path along which a unit positive charge tends to move. Do these electric lines of force are always a straight line? No. They can be even curved also like this. If it is a straight line, that line itself indicates the direction of the electric field. If it is a curve, then how to find the direction of the electric field? I want to find the field here. Then draw the tangent to that line of force at that particular point. That gives the direction of electric field at that point. So hope you understood. So let's see various properties of the electric field lines. So first property is based on this. That is, electric field lines, they diverge from positive charge. They diverge from the positive charge, and then they converge on negative charge. Or they start from positive charge and they end on negative charge or end at negative charge. So that's the diagram. So this is the diagram for positive charge, and this is the diagram for the negative charge. So this is the lines of force due to a point charge when positive means Q is greater than 0. Negative charge, this is when Q is lesser than 0. So what is the first property? The first property is the lines of force, they start from positive charge or they diverge from positive charge and they end at a negative charge or they converge at negative charge. And this is the diagram, and they have asked this particular diagram twice in the examination, that is, draw electric lines of force of the point charge Q when Q is greater than 0. Q greater than 0 means you have to draw this particular diagram. Next, when Q is lesser than 0, Q lesser than 0 means you need to draw this particular diagram. So only diagram, they have asked in the exam, you don't have to write any property as such. So these are the two diagrams for this particular question. So let's learn more properties. So we have learned first property. The first property is that electric lines of force, they diverge from the positive charge and they converge at a negative charge, or they start from positive charge and end at negative charge. So property number 2, lines of force, they never intersect. Why two lines of force, they never intersect? See, every line of force which we draw represents the direction of the electric field. And if I draw one more electric lines of force which are overlapped, which intersect, then at the point of intersection, we have two directions of the electric field, because every line of force indicates the direction of the electric field. And this is not possible because at a particular point, if at all there is a field, then it has to be in one particular direction, which you call the resultant. It cannot be in two different directions. So that's why two lines of force, they never intersect each other, because if they intersect each other, it indicates that at the point of intersection, we get two different directions of the electric field, which is not possible. That's why two lines of force, they never intersect each other. The property number 3, they are continuous curves without any break. See, whatever the line that we have drawn, we draw like this, continuous line. Even if we draw like this, It's again a continuous curve like this. They are continuous curve. There is no break like this. If there is a break, it indicates that the field is discontinuous, which is not true, because the field is continuous, it's extended till infinity mathematically. Every field for that matter. It can be gravitational field, it can be even the electric field. So it is a continuous curves without any break. Okay, that's property number 3. So these are all important properties. As I've told you, the question has appeared a number of times in the examination. And now property number 4. They do not form any closed loops. So if I consider a bar magnet, in the case of bar magnet, the magnetic field produced by the magnet exists both inside the magnet as well as it exists even outside. So that if at all I have to draw the line of force due to a bar magnet, I have to draw the line of force which is something like this. Now this is called closed loop, because the field exists inside the magnet as well as outside the magnet. But in the case of electric field lines, they do not form any closed loop. They don't form any closed loop like this. The reason being, there is no electric field inside a conductor. If I take a conductor, there is no electric field inside a conductor or inside a charged conductor. So that's why they do not form any closed loops. So these are the important properties of electric field lines. So let's very quickly revise those properties. Property number 1, lines of force, they start from positive charge and they end at negative charge. The next property, they never intersect each other. The next property, they are continuous curves without any break. And property number 4, they do not form any closed loops. So important question, and do study these properties and even the definition of what is electric field line. So what is an electric field lines? It's an imaginary path along which a unit positive charge tends to move. Now we can draw lines of force due to 2 charges now. Due to one charge, I have already drawn lines of force. This is due to single. So what are the kind of lines of force that we get when we take 2 charges? Let's take a positive charge here and then another positive charge. If I try to draw the lines of force due to each, then I should be drawing the lines of force something like this. But we have to keep in mind that at this region, you can see they overlap each other, which is not possible. So therefore, how to draw the lines of force due to both? Not only that, at this particular point, the fields are in opposite direction. Correct? One field is in this direction, another field exactly, and at the midway, there is no electric field. So that means there is no net electric field at this particular region, and when there is no field, we don't draw any lines of force. Then the resultant of these two, one field and this field, will give you exactly downward. Even the resultant of these two you will get exactly in the upward. And based on that, we draw the lines of force, which is something like this. Without overlapping, you need to draw the lines of force. So this is the lines of force between 2 positive charges. one positive, another positive. Okay. So this is, and this indicates, you can see here there is no lines of force. Why there is no line of force here? Because that is a region of zero electric field, and we call such a point as a null point or electric neutral point. What is electrical neutral point? At a point where the resultant electric field is zero is called electric neutral point. Similarly, the lines of force between two unlike charges. The first one is between two like charges. We have taken two positive charges, and the next diagram is between two unlike charges. So the first one is a positive charge, the next is a negative charge, and the lines of force, they originate from the positive and then they terminate on the negative. And here there exists a field, they don't get cancel each other. So this is how we draw the line of force due to positive and negative charge. So here we can write like this: if this is Q1 and if this is Q2, then here Q1 into Q2 greater than 0. Q1 into Q2 greater than 0. Again here also, if this is Q1 and if this is Q2, their product Q1 Q2, Q1 Q2 lesser than 0. So product greater than 0, product lesser than 0. And again, what is the nature of the force? When the charges are like charges, the nature of the force is repulsion. So that is what you get to see, the lines of force that tend to move away, they tend to deviate. So that is what we get to notice in this first diagram. Q1 into Q2 lesser than 0. The charges are unlike. So what is the nature of the force? That's attractive. So the diagram again signifies the attractive nature of the force between the two charges. So a question can be asked based on this: draw the lines of force between two charges where the product Q1 Q2 is greater than 0, and then when the product is lesser than 0. So that's the diagram which you need to draw. Based on these electric field lines, we can measure a physical quantity, and it's called electric flux. So what is how to measure this electric flux? Electric flux of electric lines of force, the electric flux, the number of electric lines of force passing normally through a given surface is called as electric flux. The number of electric lines of force passing normally through a given surface is called electric flux. Now to understand this, let's consider this particular diagram. Greater the number, what this indicates, the number of electric lines of force passing normally. Normal means perpendicular. Okay. If more lines of forces passes through a given surface normally, then the flux is a more. So here I have represented uniform electric field. Why the field is uniform? Because the lines of forces are parallel and equally spaced. In that, I am going to consider an imaginary surface like this. This is the imaginary surface. And this is the normal drawn to it. Normal means perpendicular. And now that normal and the electric field, it makes an angle theta. So theta is the angle made by normal to the surface and the electric field. So how to measure the electric flux? Delta phi is the symbol used for electric flux. Delta indicates flux through a small surface. Electric flux is measured as the dot product of electric field and area vector. So, how do we measure? Electric flux is the dot product of electric field and area vector. Moment it is a dot product, the quantity has to be a scalar. So, electric flux is a scalar quantity. How to write the magnitude of it? Delta phi is equal to dot product means it's a E delta S cos theta. That is how we write the dot product of two vectors. It is the product of the magnitude of the two vectors and cosine of the angle between them. So, what we get to notice here is E is a vector. Delta is here, it's area, but here it's an area vector. So, what is the direction of an area vector? The direction of the area vector is normal to the surface, normal, and then outward. If this is a surface and if I am facing the surface, then it is normal means perpendicular, and then it is outward towards me. If this is the surface and if we are facing the surface, then it is normal, normal means perpendicular, and then outward like this. So, therefore, in this diagram, this is the surface and this is the normal to the surface. So, that itself is the area vector. So, therefore, E and delta S are the two vectors and theta is the angle between the two vectors. So, that is how we measure it. So, flux is the dot product of electric field and area vector. And how do we define electric flux? The number of electric lines of force passing normally through a given surface is called as electric flux. So, flux depends on mainly three factors. One, electric field, area through which we measure the flux, and then the angle between the two. So, let me consider two cases, case 1 and case 2. So, this is the electric field which is E. The surface which I have taken is here. Now, the surface can be of any shape, remember. Now, in this diagram, where is the area vector? Area vector is always perpendicular to the surface, normal to the surface and outward. The surface is this. Perpendicular means it's like this. So, area vector is outward and then normal. So, it will be like this. Outward it is, okay, it's like this. So, when it is outward, the angle between the area vector and the electric field is 90 degree. So, in this case theta is 90 degree. So, I am going to consider the same. This is the electric field. The surface is here. So, here the same surface, if you rotate it like this, then we get it like this. In this, area vector will be like this along. This is the direction of the area vector. This is the direction of the electric field. So, here both area vector and the field are along the same direction. So, what is the theta in this case? It is 0 degree. Now, let us find when theta is 90, cos 90, it is a 0. So, the flux is minimum. Theta 0, cos 0, 1, flux is equal to E delta S, which is maximum. So, when electric flux is minimum. Flux is minimum when area vector is perpendicular to the electric field. When area vector is perpendicular to the electric field. When flux is maximum? Flux is maximum when area vector is parallel to the electric field. Okay. So, when area vector is perpendicular to the electric field, the flux is minimum. When the area vector is a parallel to the electric field, the flux is maximum. So, what is the maximum value of the flux? It is E into delta S, where what is E? Electric field. What is delta S? The value of this area. So, this is an important equation which we will be using it later in some of the derivation. Okay. Now, what we have measured here is a flux through a small surface, and important that whenever we measure flux through that small surface, we have to assume that this E electric field has to be same at each and every point on the surface. So, that is the conditions. While measuring the flux, make sure that the value of the electric field is same at each and every point on that surface. Only then we will be able to measure the flux through a given surface. Suppose if we have a large surface where electric field is same at each and every point, then how to measure the total electric flux? See, this is the flux through a small surface. If you want to measure the total electric flux over the entire surface, then total electric flux is given by algebraic sum, that is summation of E delta S cos theta. So, the difference between this equation and this equation is that this is used to measure the flux through a small surface, and this is used to measure the total electric flux through the entire surface, phi total electric flux. Summation indicates adding all the flux that passes through the surface. So, hope you have understood the concept electric flux. So, therefore, electric flux is basically measure of electric field. See, flux is a measure of electric field. More electric field means there is more flux, less electric field, less flux, and if there is no electric field means there cannot be any flux. That is how the flux and the field are related. So, how to define electric flux? The number of lines of force passing normally through a given surface is called as electric flux, and we have the vector form here. This is the flux through the small surface, and this is the total electric flux through a large surface. So, there is one more question that has appeared in the exam this year, March 2020, and the question is, what is the SI unit of electric flux? So, to find the unit of the electric flux, I have to find the unit of electric flux. What is the unit of electric field? Electric field is Newton per Coulomb. This is the area. Even though it is a vector, area has the unit meter square. So, there we are with the unit, it is a Newton meter square, you can write up per Coulomb is the unit, or you can even write it like this also in the exam. So, Newton meter square per Coulomb is the unit of electric flux. In this equation, we get to see that flux is related to electric field. Electric field in turn depends on the charge. And that relation between the flux and the charge is given by a theorem, and the theorem is called Gauss theorem. Again, you will find almost 1, 2, 3, 4, 5 times this question has appeared. State and explain Gauss theorem. So basically, what does Gauss theorem relate? It relates electric flux and the charge, because flux is related to electric field is related to the charge, and that's why the flux is in turn related to the charge. So I'm going to give the mathematical form of this particular theorem so that it's very easy to state the theorem. So what is the mathematical form of the Gauss theorem? It is total electric flux through a closed imaginary surface in free space or in vacuum is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. So that is the statement. So what is the statement? Check this. Phi total. The total electric flux through a closed imaginary surface. It has to be closed surface, and it is imaginary because whenever we consider surface, we don't consider the real surface. We consider always the imaginary surface, right? So the total electric flux through a closed imaginary surface in free space means in vacuum, okay, is equal to 1 by epsilon naught times, product times, what is this Q, times the net charge enclosed by the closed surface. So therefore this Q has to be the charge present within the surface enclosed. Okay, let me consider plus Q1 which is equal to, or Q1 which is equal to plus 2 coulomb. There is a Q2 which is minus 3 coulomb. Q3 minus 4 coulomb. Q4 plus 6 coulomb. Okay. So now I am going to consider a closed imaginary surface which can be of any shape. See, this is closed, imaginary surface, closed, so that the charges are enclosed. I am going to consider Q5 also, which I am going to consider outside the surface, which is plus 3 coulomb. Okay. So this is the closed imaginary surface, and this imaginary surface is called as Gaussian surface. What do we call? Gaussian surface. The closed imaginary surface is called as the Gaussian surface. And through this surface, I want to measure the total flux. So therefore, the total flux is given by 1 by epsilon naught times, what is Q? The total net charge enclosed by the closed surface, the one which is enclosed within that only. So that means it's Q1 plus Q2 plus Q3 plus Q4 only. We don't consider this. Why? Because it's outside the surface. Only those charges which are enclosed within the surface are to be considered, not the one which is outside. So let's substitute 1 by epsilon naught. What's a Q1? It's a 2. What is Q2? Minus 3. What is a Q3? That's a minus 4. What is a Q4? It's a plus 6. Plus 6. That's 1 by epsilon naught. So we have 6 and then 2. That's 8. And 8 minus 7 is a plus 1. Correct? So last time I had made a mistake while adding the charges. So hope you have understood where exactly. That is plus 4 coulomb and minus 2 coulomb. I had written it as minus 2 coulomb. Hope you know in which topic I had made that mistake. Okay. So, no more mistake again. So, therefore, this is 6 plus 2, correct, that is 8, and 8 minus 7 is a plus 1. So, this is how we can apply the Gauss theorem here. So, I am going to consider one more example. I am going to take 8 electric dipole. How many? 8. So, this is the closed imaginary surface, and I am going to consider 8 electric dipole, okay, and I want to find the flux, total flux. So, total flux through a closed imaginary surface in free space is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. What is an electric dipole? An electric dipole is nothing but a pair of equal unlike charges. So, that means if I take one electric dipole, it is a pair of equal and opposite charges. So, that what is the net charge of an electric dipole? Net charge, it is a 0 plus q minus q, that is for 1. That means even if you take 8 or 80 or 800, the net charge will be always 0. So, this will be 0, and when that is 0, what is the total flux? It is 0. So, the total flux through a closed surface enclosing any number of dipole is always 0. So, this is how we apply Gauss theorem, an important theorem, as you can see repeatedly asked a question. So, what is the statement? Let us repeat that statement. The total electric flux through a closed imaginary surface in free space is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. So, what is the meaning of that enclosed by the closed surface? You have to consider only those charges which are within the surface and not outside the surface. So, we have analyzed the 3 equations today. They are all important. The first one, the flux through a small surface. That is delta phi is equal to E delta S cos theta, where theta is the angle between 2 vectors, electric field vector and area vector. Okay. And what is the direction of area vector? Always perpendicular to the surface and then outward. And if you want to measure the total flux, phi total, then go for the summation E delta S into cos theta. So, this will give you flux, total flux, this will give you flux through a small surface. And then the last one important theorem, which is the Gauss theorem. This also will give you the total flux, total. So, total electric flux through a closed imaginary surface in free space is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. So, hope you have understood all the topic that I have explained, and in the next class we are going to derive some equations based on all these 3 equations, that is applications of Gauss theorem. There are about 3 derivations are there that ends the chapter, and after that we are going to have the test in this particular chapter called electric charges and the field. So, start revising all the topics by going through the entire video, the study material which I have already provided, revise, and revision means write and then practice. That is the only way to remember all difficult topics. So, I will continue the rest of the topic in my next class. Thank you.